In this video, we will be discussing a conceptual model of the components that, when taken together, explain any individual's observed score on a measurement for a one-way between subjects analysis of variance. It is called the factor model of individual scores. This is a somewhat more advanced topic than we have covered in our prior videos, and some introductory statistics courses may not include it when one-way ANOVA is covered. Therefore, you can skip this video and move on to our subsequent videos on analysis of variance if you wish, as those videos will not require an understanding of this topic to fully benefit from them. However, this is an important topic for those students who plan on taking more advanced statistics courses in the future. For those of you who want to continue with this lesson, all you will really need to benefit from it is a basic understanding of what a one-way between subjects ANOVA is. As a reminder, a one-way ANOVA is a statistical technique which evaluates the effect that a single independent variable has on a dependent variable. The single independent variable in the study will have two or more different levels or groups associated with it. For instance, if the independent variable you are studying is reaction time, you might be interested in knowing whether the mean reaction time to video stimuli, audio stimuli, or a combination of both is different. A between subjects ANOVA is one in which each subject in the study is only exposed to one of the levels of the independent variable. There are other, more complex models that are used to describe individual scores in ANOVAs that contain more than one independent variable, but we will not be covering them in this video. The factor model for individual scores is a statistical representation of the data that decomposes the individual scores into three different components. These components are 1. The overall, or grand, mean designated by the Greek symbol mu. 2. The effect that being assigned to a particular group in a study has on an individual's score, designated as alpha. And 3. A term that represents random error in that score, designated as epsilon. Taken together, these components form what is called a linear structural model. The model says that an individual's score on an outcome measurement can be broken down into these three components that can be evaluated independently, and when added together, completely account for an individual's score. The model simply says that any score, which is notated as y sub ij, can be decomposed into these three different parameters. 1. The grand mean, mu. The grand mean is the average of all the scores in the population. 2. A treatment effect, alpha sub j, which is the effect that being in a particular treatment group, j, has on the individual's score. Some texts use the Greek letter tau to represent a treatment effect. In this context, treatment doesn't necessarily mean that we performed some kind of experimental manipulation on the group members. It simply means that the group members had some type of defining characteristic, such as age or gender, referred to as a treatment that differentiates them from the members of other groups. We will say more about this shortly. 3. Error, epsilon sub ij, which is anything else that affects the score of individual I, in group J, such as inter-individual differences, intra-individual differences, and lack of experimental standardization. Here are some details about the components in the model. The grand mean, mu. This is a constant and the same for everyone in the population. It is the starting value or reference score from which an individual's score will be either raised or lowered as a result of whatever treatment group the participant is assigned to. Numerically, it is the average of all the scores in the population of interest and is estimated by averaging all the scores from all the samples in a study. The grand mean is not a value that is usually interpreted in ANOVA, but it is a value that is used in the ANOVA calculations. We will have more to say about why the grand mean is a parameter in the model shortly. The treatment effect, alpha sub j. A treatment effect is the effect that being in a particular group, J, has on an individual's score. The name is something of a misnomer because it implies that the experimenter subjected the participants to some kind of active experimental manipulation that was different for each group. While this is sometimes the case, it isn't always. For instance, we could perform an ANOVA to see if reaction times vary by age group. In this case, the different treatment groups would simply be made up of individuals in different age groups. For example, 20 to 40, 41 to 60, 61 to 80. The different treatments would be the age group category that the participants were grouped into. The experimenter did not actively perform any type of experimental manipulation on the participants. They were simply grouped by age, and reaction time was measured. In other cases, a treatment could be different experimental manipulations performed on groups of participants. For instance, it could be a particular teaching method if the research was designed to study the effectiveness of different teaching methods, or it could be a particular dose of a drug designed to reduce blood pressure. Like the grand mean, the treatment effect is assumed to be the same, a constant, for every individual in the same group and represents the increase or decrease in an individual's score over the grand mean that results from being a member of a particular group. In a population, it is defined as the difference between the group mean for a specific group, alpha sub j, and the grand mean, mu. Because it is defined as a deviation score from the grand mean, that is, the numerical difference between the group mean and the grand mean, the sum of the treatment effects for all the conditions in the study will always be zero. This is actually a requirement or constraint in order for the mathematics behind ANOVA to work. As we said, the meaning of treatment effect is clear when we are performing a study where the groups are treated differently, such as receiving different doses of a drug. But it is less clear when the study is examining the differences between intact groups that do not undergo a specific experimental manipulation. Here is a simple example that will clarify this concept. Let's assume an alien species who had no prior experience with humans was interested in whether human height differed by gender. It turned out that the grand mean of human height was 64 inches. The average height of the group women was 62 inches, and the average height of the group men was 66 inches. We have defined a treatment effect as the difference between the group mean and the grand mean. So in this example, the treatment effect for men would be 66 minus 64, or 2 inches. What this means is the treatment effect for being in the male group is plus 2 inches. Likewise, the treatment effect for being in the female group would be 62 minus 64 equals minus 2 inches. So on average, if we used the grand mean as the best prediction of human height, assuming that we had no other information, being male would raise the predicted height by 2 inches from the grand mean, while being female would lower it by 2 inches. The third component in the model is error, epsilon sub ij. Error raises or lowers each person's score on the outcome measure in a random and unpredictable fashion. It is formally defined as the difference between an individual's score and the mean of the group that the person is a member of. This should look familiar, as it is how we start to calculate the variance of a group. We begin by subtracting the group mean from each person's score. What this says is that if there were no error, everybody within a given group would have the same score. The group mean. Error is caused by the three processes we discussed earlier: inter-individual differences, both random and systematic, intra-individual differences, and lack of experimental standardization. Across the entire population being studied, these error effects are considered to be a random, normally distributed phenomena, with a mean of 0 and a variance equal to the error variance in the population. Our simulation program is a tool that allows us to simulate and visualize the workings of the factor model of individual scores. This tool will enable us to demonstrate how we mathematically model the scores in 3 populations of 3,000 individuals each. For the purposes of these simulations, we will often be referring to each population as a group so we can clearly differentiate among them. For these simulations, we will be modifying 2 of the group parameters, the mean and the variance, so we can see the effect they have on the individual scores. We will be able to examine all the elements of the factor model under different conditions. Here are the parameters that we will be varying. The group means. This parameter represents the average scores across all the individuals within each of the 3 groups. We can set the group means to any values we wish, allowing us to create scenarios where the group means are the same, indicating no treatment effect, or different, indicating a treatment effect. The variance. This parameter represents the variability of individual scores within each group. We can set the variance to any value we wish, including 0, which would indicate no variability or error within a group, or to a higher value indicating a greater degree of variability or error within groups. This will allow us to model random error variance for all the individuals within the groups. The simulator will generate individual scores based on these parameters using the factor model for the scores. So, for each individual in a group, their score will be determined by adding the grand mean, the treatment effect for their group, and a random error term that will be unique to them. First, the grand mean is calculated by averaging the three group means that we set at the beginning. Because all groups are the same size, this value is the same as it would be if we just averaged all the scores. Second, the treatment effect for each group of scores is calculated by subtracting the grand mean from the group mean. This value represents the extent to which the average score in a group deviates from the grand mean because of a treatment or group level effect. Third, the error term for each individual is produced by generating a random number drawn from a normal distribution with a mean of 0 and a variance equal to the population variance that we set. This process introduces individual level variability into the scores. This is the way we simulate the fact that error is a random phenomenon that is different for every individual. The larger we set the variance, the larger the random error score will become for each individual. The mean of the individual errors within the groups will always be 0, and the variance of the individual errors will always be equal to the variance we set for the group variance. By adjusting the means and variance and observing the resulting individual scores, we'll be able to gain a deeper understanding of how the grand mean, treatment effects, and random error combine to provide a model that explains those scores. As we have discussed, the factor model of individual scores allows us to break down each person's score in a one-way ANOVA into three different components: the grand mean, the treatment effect, and random error. Our first simulation will consider the case where there is no treatment effect and no random error. In this simulation, we will set the means of all three groups to 100. When the means of the groups are all the same, this indicates that there are no treatment effects. We'll also set the variance of the groups to 0, which indicates that there is also no error. Let's take a look at the results. As a reminder, the factor model states that the score for individual I in group J, notated as y sub ij, can be expressed as the sum of the grand mean, mu, the treatment effect, alpha sub j, and random error, epsilon sub ij. In this case, since the means of all the groups are 100, the grand mean mu is also equal to 100. The treatment effect alpha is defined as the difference between the group mean and the grand mean. However, because our group means and grand mean are the same, our treatment effect is 0. Finally, the individual error term, epsilon sub ij, represents the variability within each group. But we've set our variance to 0, so there's no variability, and each individual's error term is 0. Therefore, under these conditions, our factor model simplifies to y sub ij equals mu plus 0 equals 100. So, as you can see, when there is no treatment effect and no error, all individual scores are equal to the grand mean, which is a constant. In this case, every individual in each group has a score of 100. This illustrates our first concept. Without variation or treatment effects, all scores in each group are identical and equal to the grand mean. For our second simulation, we'll add a bit of complexity by introducing a treatment effect. To do this, we'll set the group means to different values, but we'll keep the error set to 0. We will set the group means to 95, 100, and 105 for each of our three groups respectively. Remember, the variance is still 0, which means there's no variability within each group. But let's consider how our changes affect each component in the model. The grand mean is the average of our group means. So in this case, it's 95 plus 100 plus 105 divided by 3 equals 100. This time, there are treatment effects present. The treatment effect, alpha, is the difference between each group mean and the grand mean. So for our three groups, the treatment effects are -5, 0, and +5 respectively. The error term, epsilon sub ij, remains 0, as there is no variability within each group. So for an individual in the first group, their score would be calculated as follows: 100 minus 5 plus 0, which equals 95. For an individual in the second group, the score equals 100 plus 0, which equals 100. And for an individual in the third group, their score equals 100 plus 5 plus 0, which equals 105. As you can see, when there's no error in the model and there are treatment effects present, all the scores in each group are equal to the group mean. This indicates that every individual in the first group will have a score of 95, in the second group 100, and in the third group 105. This demonstrates our second concept. When there is a treatment effect but no error, all individual scores in a group are equal to their group mean, which is a constant for each person in each group. It's the treatment effect that causes the means to differ between groups. Next, we will introduce some variability within the groups by setting the variance to a non-zero value and observe how this variability affects individual scores within the groups. For our third simulation, we'll set all the group means to 100. The variance of the groups will be set to 225, which will add random error to each of the scores. With our new settings, the components of this model are affected as follows. The grand mean mu remains 100 since all group means are 100. The treatment effect, alpha sub j, is 0 since all group means are equal to the grand mean. For each individual, the error term, epsilon sub ij, is set to a random value drawn from a normal distribution with mean 0 and variance of 225. Hence, each individual's score becomes 100 plus 0 plus their individual random error score, which is no longer 0. This indicates that each individual's score is equal to the grand mean plus their error term. The error term introduces random variability within each group, so the scores of individuals within a group will now differ from each other. You can also see that the error term in the model is equal to the difference between the individual's score and the mean of the group to which the individual belongs. The population variance we set at the start, 225, is directly responsible for the variability we see in the individual scores. For our fourth and last simulation, we will introduce both treatment effects and error to see how they jointly influence the individual scores. We will set the group means to 95, 100, and 105, and the variance to 225. This will introduce two sources of variation that is due to random error, and variation that is due to treatment effect. Our factor model remains the same, but now all three components of this model are in play. The grand mean mu is equal to 95 plus 100 plus 105 divided by 3, which equals 100. The treatment effects, alpha sub j, are minus 5, 0, and 5 for each of the three groups respectively. The error terms, epsilon sub ij, are random values drawn from a normal distribution with a mean of 0 and a variance of 225. So the score for an individual in the first group becomes 100 minus 5 plus error, which equals 95 plus their individual error value. For an individual in the second group, their score becomes 100 plus 0 plus their individual error value. And for an individual in the third group, their score becomes 100 plus 5 plus error, which equals 105 plus their individual error value. In this scenario, each individual's score is influenced by both the treatment effect for the group to which they are assigned and the random error term for their score. This demonstrates our final concept. Each individual's score can be modeled by the sum of the grand mean, the treatment effect for their group, and their individual error term. The treatment effect and error term each introduce a different source of variability into the scores. The treatment effect causes systematic differences between groups, which will be reflected by the variation in their group means. The error term represents the random variation within each group regardless of the presence or absence of treatment effects. The variance of each group reflects this random variation of individual scores and is assumed to be equal across the populations measured. Having said this, there is one caveat about which we need to remind you. In this video, we have been discussing the modeling of individual scores as it applies at the population level. As we said earlier in the video, when we used the term groups to describe the scores, it was for descriptive convenience, but we were actually referring to population-level data. When we conduct an analysis of variance, we are dealing with random samples drawn from those populations. Because of this, there is another source of variation in the scores that we have to consider. As you have learned from our previous videos in this series, that source of variation is sampling error. So while it is true that at the population level, the treatment effects are fully responsible for the differences in the means of the populations, when we take random samples from a population, we are estimating the treatment effects using the means of those samples. If we took another set of samples from the same population, our estimate of the treatment effects would be different. Therefore, in the sample data, the differences between the group means result both from treatment effect and sampling error. As you will learn, the goal of analysis of variance is to estimate how much of the differences between the sample means are due to sampling error and how much is due to treatment effects. It is these estimates that enable us to draw conclusions about whether the differences in the sample means were more likely to be due to random error or to the effect of experimental treatment. This concludes our video on the factor model for individual scores in a one-way between subjects analysis of variance. We hope that you found our presentation and simulations informative. Thank you for watching.